Yeah, well, I think that I can let me first introduce the speaker. That we are delighted that this ASSP seminar will feature Jiezhong to present MoBA, mix of block attention for long context large language models. Jiezhong is a professor at the Hangzhou Institute of Medicine at the Chinese Academy of Science. He got his PhD degree from Tsinghua University in 2022 under the supervision of Professor Jiezhong. His research interests include AI for science and long-context large language models, and received the 2022 CKDD Dissertation Award running up. Yeah, I think Jiezhong can share the screen and start today's talk here.
Sure. Uh,
Yeah, we
okay.
can.
Um, I'm very glad to be here to present MoBA. Um, oh, oops. Yeah. MoBA is a recent work in um, training time dynamic block attention for long-term context large language models. And here is the paper link and the code link. Um, okay. So this is actually a collaboration work with Kimi, with Moonshot.ai, and a lot of people contribute to this work, including uh, many researchers from Moonshot AI, and Professor Mingxin Zhang from Tsinghua University, and I'm Jiezhong Qiu from Hangzhou Institute of Medicine. Actually, I'm an AI for science researcher nowadays, but I also I'm also interested in long context large language models. So this is actually a side project of mine. Uh, uh, okay, so so I want to briefly introduce MoBA. So first, we are very familiar with the full attention. So suppose we have one query tokens and a bunch of uh, key and value tokens. So the full attention actually compute the query token, the inner product of query token and each key token. And we have a softmax to normalize these attention scores. And finally, we weight the sum to aggregate the value tokens. So the challenge lies when the number of key and value tokens grows to, let's say, 100,000 or even 1 million. In that way, we have to compute a lot of attention scores, and which can be very time consuming. So the idea of MoBA, not only the idea of MoBA, but the idea of sparse attention is that we only select a very small subset of key and values to compute the attention. So we have a function here, I, to indicate which part of the key and values we want to select uh, for the computation of sparse attention. And the key innovation of MoBA is that we partition the context into several blocks. And here B is the block size. And this one indicates the ice block. So we only want to select a subset of blocks. And here we have a gating function GI indicate which blocks we want to select for computation. And GI is actually controlled by a score function SI. Here we implement SI to be the dot product of the query token, and the mean pooling of the ice block. So it's actually very similar to MoE. If you guys um, are familiar with MoE, MoE is that we have an input token, and you have a gating network to decide which expert you want to send this token to. And suppose suppose that we have, let's say, 200 expert, and you only want to select a very small subset of expert for computation. Let's say you select two expert or three expert. So if we regard the KV blocks as expert in MOE, MOBA is basically an idea that combining block sparse attention and mixture of expert. Okay. So one work that motivates MOBA is Transformer XL. Uh, Actually, Transformer XL can be viewed as a special case of MOBA where we have a predefined gating function that we not only we choose the new segment, which is the current block here, we also choose uh, the the most recent block. This is the setting of Transformer XL. And also, Transformer XL has no grid to historical blocks. But MOBA extend Transformer XL in two perspectives. Firstly, it can choose very old blocks, not only the most recent blocks. Uh, Secondly, they are gradient flow back to the historical blocks. Okay. So another work that motivates MOBA is MOE. Actually, when I was a PhD student in Tsinghua University, I participated in a MOE project in fast MOE. Many of you may haven't heard about it, but that's in about 5 years ago, and I believe that is the one of the most earliest attempt for open source MOE. At that time, the only open source implementation of MOE is from Mesh TensorFlow, which is used to train Google's G-Shard and switch transformer. And this project is open source implementation of MOE with PyTorch and can be used in Megatron, actually in a very old version of Megatron to train MOE model in Megatron. And we actually implement what we call now expert parallel, that we placed experts in different data parallel workers so that you can have a very large expert pool support MOE training. Okay. So this toolwork is the motivated the design of MOBA. So the first idea of MOBA is to combine actually the first implementation of MOBA is based on fast MOE. We basically implement the idea of MOBA with FastMLE, and the initial implementation is that we combine MOBA with context parallel, which means that the KV blocks are actually distributed in different GPU card, and there are a lot of communications between them. And unfortunately, that's actually a failed attempt because of the load balance issue. We will mention this later. Okay. So let's come back to the idea of MOBA. Um, we actually implement MOBA with the final version of MOBA, and also the open source version of MOBA is based on flash attention. So basically, I can explain the code a little bit. So the first step is to split the KV the KV cache into blocks, and we have a mean pooling function that we compute uh, the, uh, the representation of each block. And we have the score function, which is the inner product of the query token and the block representation. So based on this, we have a top K gating, which select very few blocks for each query token. And according to the gating function, we have some very complicated index select operator to rearrange the query tokens according to their selection. And we compute uh, the attention of each block separately um, using flash attention. And the final step is to combine the attention output with online softmarks. I guess this is most steps are very straightforward, except the combine with online softmarks. So I will explain this a little bit. So suppose we have a query token, and this query token selects two KV blocks. The first KV block is I1, and the second KV block is I2. Okay, let's suppose we only select two KV block for this query token, and we compute the attention output separately. The O1 is the attention output of this query token with respect to the first KV block. This is a softmax function. Um, and O2 is the attention output of the query token with respect to the second KV block. And here, let's suppose xi to be the attention score, and LSE here is the log sum exponential function, which is actually the logarithm of the normalization function of the softmax. Okay, so the problem is that suppose we have O1, O2, and the LSE functions, how we combine it to the final results of the attention output, where where the query token is Q, and the key and values is the concatenation of the first KV block and the second KV block. Through some mathematics, you can have the final results that this is actually a weighted sum of O1 and O2. And the coefficient can be computed as follows, which is basically based on the LSE1 and LSE2. So this is the forward function, and you should also take care of the backward function to make sure the gradient is correctly computed. Okay, so this is basically the implementation idea of MoBA. So we have we will basically split the KV cache into blocks, and we, according to the gating function, we rearrange the query tokens. We send the query tokens to each KV block, and we compute the the attention output separately, and we finally merge them into the final MoBA output. Okay. So this is the speed up results. MoBA is able to scale to up to 10 million context lengths and basically achieving 10 times the speed up ratio. We in these two experiments we make sure the sparsity is above I guess it's 95%. It's above 95%. So so it's actually interesting to see that MoBA is able to scale to context length up to 10 million. And we also conduct scaling law experiments. So this first figure A here is the we monitor the language model loss. You can see the language model loss is very close between MoBA and full attention. But actually, it's actually not a good idea to monitor only language model loss, because in language model training, most of the sequences are very short sequences. So we also monitor what we call trailing and language model loss, which is the language model loss at the very end part of the sequence. Specifically, for figure B here, the training context length is 32,000, And we only monitor the language model loss of the last 1K tokens, which means that we only consider the language model loss at the position range from 31,000 to 32,000. Okay, th- so the figure B shows that there is actually a performance gap between mobile and for attention. So especially for the tokens at the very end positions of the sequence. Uh, Another design choice is the granularity of block. So if you are familiar with the MoE literature, there is uh, there's a growing trend to have very fine-grained experts. So you have each expert is a feed-forward network. So there's a trend to make the feed-forward network very small, and you select a lot of them for each input token. So we also test the similar idea that what if we have fine-grained blocks? Um, so this figure is about uh, the block segmentation strategy. We keep the sparsity as a constant, only varying the number of blocks and the top K selection. So we can see that there's an improvement when we increase the block granularity. This finding is very similar to this finding is very similar to that of MOE, and we believe that there is we believe that sorry we believe that we can test this idea in the future. Let's say what if we have a much more fine-grained expert? Um, for example, uh, each block has a context length of 100 or even below. Okay. So the another interesting observation of MoBA is the hybrid strategy. Uh, we find that MoBA can be seamlessly transferred between from or to for attention at any time. So the first hybrid strategy is hybrid training, which means that suppose you want to train a full attention model, and you can consume 90% of tokens with MoBA and only transfer from MoBA to full attention at the very end part of training. You can take less than 10% of tokens with full attention. And if we monitor uh, the language model loss of hybrid training, which is the green line here, is very close to that of full attention, which means that you can benefit from the speed up of MoBA because 98% of tokens are consumed by MoBA. Another hybrid strategy is layer-wise hybrid. Uh, this is actually due to our observation that uh, pure MoBA-based architecture can lead to suboptimal results in SFT. Uh, we hypothesize that this is because in SFT, only very few tokens have have loss, have language model loss, and most of tokens are prompt tokens, and they don't have language model loss. So in that case, sparse attention can maybe have bad behavior in backpropagation. So our solution is that we switch the last several layers from MoBA to full attention. Uh, Figure B and figure C uh, shows the results that we switch, let's say switch the final layer from from MoBA to full attention, switch 3 layer, 5 layer, 10 layer. So, and the results shows that the more layers we switch from mobile to full attention, uh, the better performance we achieve. And we believe that switch 3 or 5 layers from mobile to attention is a good solution to balance the performance and the efficiency. Okay. So finally, we apply mobile to the continued pre-training of a Llama uh, Llama 3 model. So this is the post-training recipe. We basically follow the uh, from short to long strategy. That is, we start from Llama 3, and we conduct 200,000 continued pre-train, and uh, and 500,000 contact lens continue pre-train until 1 million contact lens continue pre-train. And then we conduct the SFT procedure, and finally we have the instructor model. And we test the performance in many standard benchmarks. You can see that the performance gap between mobile and full attention is actually very small. And finally, the final experiment is the popular needle test. Mobile can achieve a very good performance from short contacts to long contacts, up to the contact length of 1 million. Okay. So this actually the above content can actually you can find them in the mobile paper, and we will discuss some failed attempt of mobile. If you have noticed the article in Zhihu, you may have read some of them, and we can have a more detailed discussion of this failed attempt of mobile. So at the very beginning of mobile, we actually implement a very similar to the the original architecture in the attention all you need paper, which is a cross attention plus self attention plus FFN architecture. And we separate the attention to the current block and the attention to the historical block. You can see that in the cross attention part, the query token is the token set in the current block. And the KV tokens are the tokens from the historical block. And we have a gate to control which KV to select for input token. And after the cross attention layer, it is the self attention layer, which we only focus on the self attention within the current block. And finally, is the FFN layer. So what is the bad point of this architecture? The main bad news is that we introduce a lot of new parameters. So the cross attention, we add about 1/3 of the parameters to the model architecture. So if we want to conduct continued pre-training, it will lead to instability because we add too many new parameters to this model. The next version of mobile is that we conduct a MOE style weighted sum. So what is the MOE style weighted sum? It's actually follows the MOE strategy that for each expert we compute the output separately, and we weighted sum them. We aggregate them with the gating function, with the output of the gating function. And that's the we call it mobile V1. We want to have involve the gating function in the computation of mobile, and we also observe instability during training. So we have to discard the gating function from the current mobile implementation. And we replace this weighted sum with the online softmax strategy, which we mentioned earlier. So the weighted sum, the aggregate function here, the weighted coefficient here is finally computed according to the online softmax instead of the output of the gating function. Okay. Uh, we actually also tried to combine mobile with context parallel. The basic idea is that we distribute KV blocks in different context parallel workers in Mactron so that we can support a very long context length. Um, but bad news is that is the load balance problem. Uh, this figure is borrowed from the M inference paper, uh, who noticed that the attention map shows very interesting patterns. One of the common pattern is what they call A shape. This phenomenon is also uh, observed by papers like attention sync. Basically, uh, they observe that the most recent token and the most early tokens are most frequently attended. So this actually lead to a load balance problem. You can imagine that. What if we we partition the KV blocks in different workers, and the first worker have a lot of load balance, has a lot of workload to compute. This is a very unfair problem. A lot of other workers, they are idle, and the worker zero, which handle the attention sync, have to consume a lot of the query tokens. So we have to take one step back about the context parallel idea. So in current mobile implementation, the four context lengths are stored in one GPU. Okay. So I think that's the all about my talk today. Uh, I guess you may have some questions.
You can either unmute yourself or just put the question in the chat. Yeah, I think I have one question just about how mobile deal with inference or decoding time. Yeah, because for the decoding that we need to gradually generate new tokens, and
Mhm.
not want to maybe cause mean pooling every times. Just I want to do you have some special data structure to maybe store maybe some values about from the mean pooling? Yeah, do you have some data?
Uh, uh, it's actually a good question. The pooling function can be maintained with the growing of KV cache, actually. So you don't have to compute every time you want to decode the nectar token. Uh, but uh, one observation is that when we use mobile with multi-head attention, there is no significant speed up because each attention head can have its own block selection. So if you union all the head, the block selection can cover a very large part of the KV cache actually, which lead to a significant amount of KV IO.
I
Uh,
see.
but if we use mobile in uh, group GQA or MQA, it can lead to significant speed up because all the we can force the we can force that because in GQA or MQA the KV block selection across head is much more similar than that of MHA,
I see.
and we are not testing this idea in MLA.
You mean that even you do not force maybe query heads from the same group to select the same query blocks, they still have a similar selection? Yeah.
Yeah, yeah. If we yeah we consider we count the selection pattern of GQA and MHA, and we find that even we we do not force different attention head to have the same uh, block selection. They tend to have the same selection pattern across heads. Yeah.
Have you tried, for example, in a reversed direction that, for example, you have one query head and you select from two KV heads? Do they are similar again, or they are just not similar to each other? Yeah. Because probably
Uh,
previous one, I guess that if only the KV heads from the if only the core heads from the same group that share a similar selection, maybe the KV heads design the selection. Yeah,
that's a good idea. We will definitely try this.
I see. Yeah. So what's your idea about the NSA? Because they are actually doing head sharing.
One strategy we are trying is that we introduce some forced selection rule that we want to force that uh, the each query each head we will partition the KV heads into groups, and we force that in each group they have the same selection strategy, and we do observe some positive results.
So this basically becomes native sparse attentions
Oh
mechanism.
yeah, that's actually inspired by native sparse attention.
Yeah, so you indeed found, okay, native sparse attention strategy works in practice.
Yeah. That's actually true. And but we still need to partition the KV heads into groups. Uh, it's if all the KV heads shared some selection pattern, that's also hurt performance a little.
Um, so how many groups does the model require to achieve good performance? Because I observed that so in native sparse attention they have four group, right? So and each group is like 16 height, so they have 64 height, which is a big number.
Mhm. We observe the group number is different from is different for different attention mechanisms, uh, and we are now switching to from multi-head attention field, from multi-head attention to field from to MLA. So the selection strategy may be different.
I see.
So for multi-head attention, uh, if we do not introduce any constraint, the selection pattern can be really random. I mean, different head have very different selection pattern. But for MLA, the selection pattern seems much more similar.
Okay, so maybe DeepSeek folks observed that such a phenomenon in MLA, and they just decide to force such restriction in their native sparse attention.
Yeah, true. That's maybe a side benefit of MLA.
Yeah, I think there's a question from the chat. As I see that MoBA still needs to store all the KV cache. Why not build a model which is native sparse to pruning unnecessary KV cache?
Uh, I think that's another direction to explore, especially in inference time. You can maintain an CPU offloading strategy. You can count the number of times each KV block is selected, and you can offload um, the KV blocks that are not frequently selected to CPU. That's and uh, is this the idea that mentioned by the chat?
Uh, Yeah, so you think offloading is a good way to solve the memory problem of the dynamic sparse attention? Yeah.
But you still need to store all the KV cache somewhere. You are want just to discard unnecessary. Um, I think that it was worth training, but it will definitely lead to a performance drop because you never know which KV block is the true unnecessary KV block. It may be sometimes be used in the future.
Yeah, but some people that they told me that they think that the key or key blocks are just something that a combination of dynamic sparse and static sparse, or not maybe just it means that some key tokens that they may not use for all the contexts. Have you maybe measured, for example, a key block to see that how many times that it may be called? Yeah, do there some key blocks that they are only called that in a local region?
Uh, we actually have some monitor of uh the hit frequency of KV blocks, and there is actually a pattern that uh some KV blocks are not very frequently called. Uh, I think this idea can be further used to improve uh, the the KV cache pruning strategy mentioned.
Yeah, but I think because the block size of MoBA is relatively larger than other dynamic sparse works, so
Mhm,
maybe
mhm,
yeah, still all the blocks need to be caught. Yeah, I guess that if that is a much smaller block size, maybe some never caught, yeah, or just caught in the local region.
mhm. Yeah, so you mean that uh, I agree that we have a relatively large block size
Yeah,
in MoBA. So that may um, delete some necessary KV cache if we pruning some blocks. Yeah, that's true.
yeah. So I was wondering, you first selected a large block size based on because that you want to do MOE style
Mhm.
in training, or you just do some observation. You find that a large block can achieve a similar performance. Yeah, which is first. Yeah,
Uh, we actually start with a relatively large block because as I mentioned that our initial implementation is based on MOE.
I see. Yeah, that
So
makes.
we start from a relatively large block size, but we have some following up experiments. Actually, the fine-grained this one to see if we have a smaller block size and more block selections, what will happen. And actually, the observation align with that of MOE. That's the fine-grained expert selection. Here, the fine-grained block selection can lead to better performance.
I see.
Mm.
Yeah,
But,
so
but,
have
but
you
in this,
tried? Yeah, I think one concerning of this curve is that if you only maybe test on some, because there are some tasks that maybe, for example, choose some things that from different positions that they may recall many blocks at one time. Yeah, so do you think it will relate it to the downstream task or the loss?
that's also an interesting point. We are testing more complicated long context tasks beyond the needle test. Yeah.
Yeah, and
In needle test, you only need to record the one position, one block. As long as you attend to the right block, you can retrieve the needle correctly.
uh,
Uh, I see your question. So if there's a multi-needle test or something like that, what will happen? Does the performance correlated to the number of blocks we select in MoBA?
yeah,
We are working on this.
I see, I see. Yeah, because that one of my past observation is that even using full attention, it is not very good at maybe multi-needle retrieval. Yeah, if using only with one query. Yeah, so I guess that maybe the model itself cannot maybe retrieve yeah, from many positions. And then for different query, because that you can have different selection, maybe it is enough. I'm not sure yet. I think that if it do not lead to performance jobs, that it will be a good observation. Yeah.
Mhm.
I have a question. Have
Mhm.
you used MoBA for non-transfer reasoning?
That's a good question. Uh, so the time we design MOBA, so I have to say that the long context learning, there's a paradigm shift from long context preview to long context generation. And when we design MOBA, our assumption is that uh, the key demand is the long context preview. So the scenario is that the user upload a very large PDF. Let's say it has 1 million tokens, and the decode stage only decode not that many tokens. But there's a trend that we also need long context decoding now. So we are testing the performance of MOBA in long time decoding, long sequence decoding. So in this experiment, in this paper, uh, we use MOBA only for preview, and the decoding stage is we also use we use full attention for decoding. So one thing we are working on is that we use MOBA to decode, and we believe that we will update this paper later. We will see more results on the MOBA decoding, and but for most of the generation tasks we examine now, the generation length is not that large. So you actually ask another question is that what if uh, we apply MOBA decoding to long generation tasks like reasoning tasks? There's a very long chain of thought to generate. And
So
we
I'm
believe that.
thinking of like regardless of the decoding efficiency, I was
Mm.
wondering what is the performance of using MoBA for such non-context decoding, like whether the reasoning result would be harmed when using sparse attention as opposed to full attention.
Uh, this is actually the ongoing work, and hopefully we can share more results in the future.
Yeah, looking forward to your new paper.
Yeah, so maybe more question about from the efficiency part that because you mentioned that in the multi-head attention that mobile maybe cannot dramatically increase the decoding efficiency. So
Mhm.
do you think that some sharing between no matter tokens or heads, I mean mainly heads, yeah, is necessary for decoding acceleration?
Yeah, I believe that introduce some restrictions across heads in the block selection can speed up the mobile decoding. Plus some very careful implementation,
I
especially for when you have to combine mobile with MLA.
We have a question from the chatting room. Jiezhong is wondering what is the difficulty in applying mobile in decoding time?
Uh, I guess you can directly use mobile in the decoding time, but the current implementation may be not efficient enough.
Regardless of the specific implementation, do you think there are like some inherent issue? For example, I believe you previously mentioned because the each head can select its own KV block, and so this would bring more I/O cost during the decoding process, and which means that the decoding efficiency is not that good comparing to like native sparse attention.
Uh, if we do not introduce any restriction in the block selection across heads, that's actually not a good idea to directly use MoBA in decoding because it's not. I I remember the efficiency is just the same as same as for attention. Uh,
Also,
yeah.
even if you use sparse activation of those block, you cannot have a large or significant speed up comparing to full attention decoding.
Another reason is that our implementation is a very naive one. We read all the KV cache and compute the mean pooling online. So uh, if that happen, the decoding stage can be very slow. So we are also implemented a efficient version of the decoding code with MoBA.
So you mean on the fly block level representation like mean pooling? So you
No, no, no.
I think this process could be done during the pre-fitting stage, and in the decoding phase, you do not need to do mean pooling.
Yeah, yeah. But you are mentioning implementation issue there. You're right.
Okay.
We have a very brute force version of the implementation of MoBA decoding. So uh, that's why we finally uh, decide to use full attention when decoding.
Yeah. So you mentioned that you have an ongoing work in using MoBA for decoding. So, uh, which means so did you ever try using MoBA for decoding during like the evaluation stage? This is I'm very interested in this question. Yeah, I was wondering why the like there's some performance degradation and
Uh, we um, so this is actually an ongoing work. So maybe we can share the results in the future. Uh,
sure, sure.
And for the hybrid part, I was wondering that yeah, because that it seems that you choose to use full attention for the last few layers. Have you
mhm.
tried some different hybrid strategy, for example, just include the mobile and full attention, or maybe just even do maybe headwise the maybe just a hybrid about mobile and full attention?
We ablate this strategy and find that replace the final layers uh, with full attention can lead to better performance in rather than interleave.
I see. It is somehow related to the UCO. Yeah, use the last few layers as full attention.
Uh-huh.
Yeah, but Yoko shared the KV cache.
Yeah.
Yeah, we
Yeah,
have another question from the
The
chatting room. What's your opinion about Yoko like model?
this is actually orthogonal to MoBA. Uh, you can replace uh, the efficient transformer part of your code with MoBA actually.
I
And
think a better application scenario would be like replacing the full attention part with
I see.
yeah, I think both phrases could be
And the second question is headwise cannot TP. Yes, you need some additional communication to synchronize the gate selection strategy across head if you using tensor parallel or DP attention.
So do you have maybe some downstream performance gap between maybe a not hybrid, a purely mobile model and the full attention? Yeah, because from the NSA, they seems to achieve a same performance. I was wondering, yeah, I see the loss gap, but I was wondering what will happen on the downstream task. Is this loss really matter a lot, or they are still performance similar?
Uh, so we demonstrated a lot here, and
Yeah.
in the needle test, basically you fail to retrieve the right needle for the if you use all layers with MoBA.
This is interesting. Yes.
I remember it's uh some pattern similar to that of lost in the middle. Basically, if it's the needle is in the middle part of this context, uh, MoBA cannot retrieve it without the hybrid strategy.
But I think full attention is also have lost in the middle problem. Yeah.
But I mean, comparing to this one, this figure.
I see, but this seems to solve almost everything.
Okay, so there is a yellow block.
Yeah, there's only one small yellow block.
I didn't
The yellow
even.
block is
Oh no no no
mm,
yeah, no yellow.
Oh.
I think
basically for if needle is in this part, uh, it will be difficult for MoBA to retrieve the for MoBA only model to retrieve.
Do you have any intuition?
Uh, this is I think it's correlated to the selection pattern. We count the selection pattern, and the block selection pattern is somehow like the A shape, similar like that. That means that the for the leading blocks, there are a lot of token attached to them, and for the recent blocks, there are certain token attached to them. But for the middle blocks, there are fewer token attached to them. So it turns out to be for the needle task is if you fail to attend to the right block, you basically cannot retrieve the right needle from the context. And for middle blocks, since there are fewer token attached to them, so the possibility that they retrieve from this block correctly is relatively low.
yeah, do you have some data like the one mentioned the few in the middle that for this one? I was wondering, yeah, I guess maybe most important information is from the starting and the recent positions, yeah, from the training data. So I do not learn well about this sparse pattern.
Uh, I think we do not explicitly have that kind of data in SFT.
I see. Yeah, because I see many long context models, they try to maybe have a ratio of a few in the middle data, just moving some part that in the end to the middle. Yeah. Yeah.
We did not engineering this procedure uh, as a lot. We just use very standard uh, continuous pre-training and SFT data just to test uh, the performance of the architecture itself.
I see. So I was wondering if it's always choose the first and recent blocks, what is as maybe performance improvement or advantage in comparison with some maybe other works such as dual attention. Yeah,
No, we haven't compared to dual attention.
I see.
Dual attention is like a static attention, sparse attention method, right?
Yeah, but it seems that it's not easy to learn the important information in the middle. Yeah.
Mm.
I think another interesting to do is that to try to add more gradient to the gate function. Uh, if you look at the current implementation of MoBA, there is no gradient with respect to the gating
Yeah.
because the block selection is a hard selection part.
Yeah, so you think that I think that two kinds of methods try to make this part differentiable. The first kind is that some people try some soft top K, and the second
Mm.
kind, like the NSA, just do attention on the compressed token that to have some gradients, which we
Mhm.
think is the most right way.
Uh, I think the soft top K1 may lead to efficiency issue in training. Uh, and the compression one uh, let me think. I think the challenge is that when you combine different blocks, how to elegantly add the gradient into the computation graph in forward pass.
Yeah,
Uh, what we have tried is that we try to directly use the gating function to aggregate the attention of different blocks, but it finally failed.
I see.
Uh,
And
So
what?
it's like dense training, sparse inference.
This is sparse training, sparse inference, but the gating function is explicitly introduced in the computation in the forward. This gating function is also a sparse one. It's a top two gating.
Okay, I see.
I see.
But the softmax is conducted within each block rather than the across all the selected blocks.
I see. So do you think that because to avoid adding the parameter that you choose using main pooling to do maybe the compression or the maybe indicator of the importance of each block, do you think
Mhm.
that we need some more advanced function for the compression itself?
But you need to firstly deal with the gradient problem.
Yeah.
You need to firstly deal with the gradient problem. You want the gating function to have gradient. Then you can design more complicated gating function.
Yeah. Have you ever tried native sparse attention's compression branch? I found that branch could provide some informative gradient and informative selection regarding
Mhm.
the like sparse block selection.
Uh, I think that's a little bit different because their gating function is uh, it's applied, not applied to the block level, but applied to the branch level. They have two strategies, and they use this gating function to aggregate the output from these three branches. But for block level, it's still difficult to have gradient,
I
if I
think
understand correctly.
yeah, so I think in native sparse attention, their compression branch is dense for every single block. So during training, every single block will receive its own gradient, no matter the block is selected or not. And
Mhm.
this could be beneficial, for example, in supervised fine-tuning stage, because you mentioned in your paper, like for MoBA, you have to have several global attention layer during the SFT stage because the reward signal is quite sparse. And maybe for native sparse attention, because of the compression branch and the reward signal is very dense, and the gradient can be backpropagated to every single token. And this could be a good strategy to make the gradient denser.
Yeah, I agree with that. Um, so I believe in the uh, let's say what if we have the next version, we can design some combining uh, compression, just like one work named infinite transformer, infinite attention. There's one branch to um, compress the historical blocks, and then there's a recurrent way to uh, uh, play with the compressed part KV blocks and the most recent KV blocks, something like that.
Yeah, this actually sounds also a viable way to provide very dense training signals.
Now, I have a more question about the efficiency part because that from the current implementation, it seems that you materialize the attention for the top K. Yeah. So that what is maybe the time consumed on this part? Yeah, because it seems that you need to materialize to select the top K.
Now, what do you mean by saying materialized?
Just I mean that because that if you want to select top K, you need to have the attention score. Yeah, I think maybe we can go.
This one.
Yeah, in the line 8 that you want to select top K, so that you have so S is materialized. Yeah, attention score. Yeah.
Yeah.
Oh,
Do you
but this
think do you
uh,
think when the sequence length is like a million level, this M term could be a potential bottleneck and because of the materialization? And because we are implementing some online top K function to avoid this situation.
do you mean that in your implementation you don't have to compute the score function, the line find one explicitly, and you can have the final top K results?
Yes, because when the M is very large and N is a function of N, and the is the function of capital N, and so basically the overall complexity is still in the order of L square, but maybe the coefficient is small. And
Mhm.
we are concerning that when the urn is very large and this turn could be a like a memory bottleneck.
Yeah. This part actually because another attention computation. When n is very large.
Yeah, so have you encountered any like efficiency issue during the pre-training? For example, when dealing with million level input sequences?
Uh, so far the efficiency bottleneck still comes from the attention computation itself.
I see, I see. So when the block size is large enough and the coefficient is like the project and the coefficient is like small enough and we can deal with it.
So since we choose the block size of hundreds of tokens, so the score matrix is at least two orders of magnitude less than the attention matrix. So that's not a problem so far.
I see, I see.
But I think it's still a little large for the 1 million case because that if the block size is 500, that
Mhm.
still will have 2000 blocks. So if you materialize it, it will be 1 million times 2000. Yeah.
But I think in this situation is okay-ish because like the input dimension. So for a single query matrix is like a million times 2000 because model dimension is at least 2000,
Yeah,
right?
yeah, it's acceptable. Yeah. It's not become the bottleneck in
Yeah,
this.
you're right. In that case, the small n is very close to the small d here.
I
Yeah,
see.
yeah, it makes sense. So the attention matrix materialization is kind of like you have an additional query term. And so for So during very long sequence pre-training, so for this S turn, so do you need some other like distributed communication to synchronize the top K selection?
Uh, so far each head have their own selection pattern, so we don't have to do that.
So
But
how do you what kind of like context parallelism were you using when encountering like very long sequence?
the current implementation, we don't have context parallel here.
Okay,
The
so
context parallel is a very early failed attempt, but we cannot handle the load balance problem.
I see. So
We finally choose not to use context parallel with MoBA.
um okay, so you are once the number of blocks are fixed, and should be computable on a single device, so you don't need context parallelism at all.
Mhm.
But what if like the input query and the input key when the sequence length is like too large and they cannot fit onto a single GPU, they must be located on different GPUs.
You mean inference time or training?
I think it's like inference time, like when the sequence length is like tens of millions, for example. And in such a scenario, for a single device, it's basically impossible to have all of those query key and value.
Uh, I think that's will be you need to somehow communicate this block representations across workers. And after selection, there are certain communications. Uh, for example, if different KB blocks are placed in different GPUs, our current implementation, you have to send the query tokens to the respect uh, GPUs that stores the KB blocks, and then send it back the output result, the attention output.
I see, I see.
There are certain communications also in this step when you want to combine the online softmax. You need to communicate uh, attention output and LSE kind of thing.
I see.
Yeah, but I think the block size is still that much smaller that if you want to that for example you put KV blocks on different devices that each device that if you want to make full use of the memory you still need to have I think I'm not know about the exact number but it seems that you still need to have some number of blocks that so maybe the selection will be still maybe not very balanced. Yeah, or maybe. Yeah, because that I think for MOE that because that their each expert is very large, so that they can, for example, put one expert on each device or something, or just a few experts. But I think for the block wise, because that is only a block size of 500, so I guess that on one device there still are many blocks.
Yeah. So do you mean that you can do some uh, load balance kind of attempt? Since in each device you can have many blocks, so you can carefully place the blocks to have some load balance.
Yeah,
Do you
I
mean that?
think that yeah, there were. I think there. I guess there are two kinds of load balance. The first is that on one device that they should have many blocks that are loaded
Mm-hmm.
within on this device, and the second thing is maybe the load balance between different devices. I think previous MOE mainly talk about the second case because that the expert size is very large. They expect that each device has maybe one expert or just a
Mm-hmm.
yeah. But I
Mm-hmm.
think it will be something different for the block. Yeah,
Yeah, that's actually different.
I see.
Uh, Another thing we try is that we try to introduce some balanced loss of MOE into MOBA, but it also hurts the performance because it seems that attention has a very strong prior uh, of the attention pattern. So if we try to add some inductive bias, we want to have that we want to that each KV block have a similar workload that will definitely hurt the performance.
Yeah, I think even for MOE, the load balancing those always hurt the performance.
Yeah, but when we add the balance loss into the mobile training, it significantly.
Uh,
So,
yeah, makes sense. Because by adding some load balancing those functions, you are forcing the model to attend those contexts that is unnecessary.
yeah, you are forcing the model to attend equally between KV blocks. That's not a good idea.
Yeah, makes sense.
And I think load balance seems to be a general question for any types of dynamic sparse. Yeah, because it seems that if you have a very long context, you have to distribute the KV cache on different devices.
Mm, um, I think that's finally could be a question, how to have a KV cache distribution strategy.
Yeah, or
Uh,
maybe offloading will win at last.
yeah, offloading strategy kind of. Mm.
Yeah, because it seems that if we distributed that the sparsity is depend on the data itself. Yeah, we cannot is a load balance, so it always exists for any kind of sparsity.
Mhm. Another design choice is that very similar to the shared expert idea in MOE, that you can somehow make the frequently attend blocks as a share experts, which means that every query token will attend to them. That's just some random thinking.
I see. I think
But
attention.
for example, the first few blocks,
Uh, yeah,
the
yeah, just like
lightning
attention sync.
blocks.
Yeah.
Yes, because I think that NVIDIA that they are recently that they are trying to make most faster communication between KV cache that from the GPU, CPU, and SSD. Yeah, so that
Mhm.
as that they bet on maybe the offloading. Yeah. Think maybe if we do not have more questions, that we can end here today. Yeah. Thank you very much for Jiezhong's talk today that we learned many details about mobile today. Yeah.
Yeah, thank you for your time.
Thank you. Thank
Thank
you
you
for your.
for answering lots of questions.